There is a scar in the hills north of Fréjus, on the French Riviera, where a dam used to stand. Walk up the dry bed of the Rayran River today, and you will find blocks of concrete the size of small houses scattered across the valley floor, some of them weighing 600 tons, thrown more than a mile from where they were poured. They are all that is left of the Malpassé Dam.
It was, when it was built, the thinnest arch dam of its height anywhere in the world, a piece of engineering so elegant that the man who designed it was the most celebrated dam builder in Europe. It did not crack under the weight of the water. It did not slowly crumble. It was there, holding back 50 million cubic meters of water, and then, in a matter of seconds, it was gone, and everything below it was gone with it. On the night of December 2nd, 1959, at 13 minutes past 9, this dam came apart, and it killed 423 people before most of them ever woke up.
I'm Dr. Michael Carter. I'm a hydropower engineer. When a structure fails this fast, the instinct in my profession is to blame the structure. Bad concrete, a thin wall, an undersized arch. But that is not what happened here. The concrete was sound. The arch was very likely the best of its kind on Earth at the time.
The thing that failed at Malpassé was not the dam. It was a single wedge of rock buried underneath one corner of it, in ground that almost nobody had bothered to look at closely. This is the story of how the finest arch dam in the world was destroyed in seconds by a flaw it was standing on the entire time. To understand why anyone built a dam here, you have to go back to France just after the Second World War. The Department of the Var, in the country's southeast, had a water problem that was really two problems wearing the same coat. In the summer, the Rayran was a dry ditch, and the region around Fréjus, famous for its early fruit and vegetables and its growing tourist trade, was desperate for irrigation and drinking water. In the winter, that same dry ditch could turn into a torrent and flood the plain below. A dam on the Rayran would solve both at once. It would store the winter runoff and release it through the dry season, and it would buffer the floods. The Ministry of Agriculture approved the project in 1950, and the Var General Council, which owned and funded the work, went looking for the best engineer they could find. They found André Coin.
I want to be honest about who Coin was, because it matters to everything that follows. He was not a corner cutter or a careless man. He was, at that point, the president of the International Commission on Large Dams, the most respected authority on arch dams in the world.
He had built dams across France, in North Africa, in what is now Zambia. He pioneered techniques that engineers still use. In 1957, standing in front of that International Commission, he could point out with justified pride that in the entire history of the form, no arch dam had ever failed. An arch dam is a beautiful idea. Instead of holding back water by sheer mass, the way a great wall of concrete does, it curves upstream into the reservoir, and the pressure of the water pushes the arch tighter against the canyon walls on either side. It carries the load sideways, into the rock, the way a stone bridge carries weight down into its foundations. Done right, it uses a fraction of the material, and it gets stronger as the water pushes on it. And Coin did it right. Malpasset's wall was around 66 meters tall, and at its base, only about 6.5 meters thick, tapering to 1.5 meters at the crest. For its height, it was the thinnest arch dam ever built. On paper, it was a triumph. But an arch dam has a condition attached to its brilliance, and Coin himself understood it better than anyone. Because the arch throws all of its force sideways into the ground, that ground has to be able to take it. The dam is only half of the structure. The other half is the rock it leans on, and that half is the one nobody sees. Coin said as much in his own lectures. Of the two dams, the man-made one and the natural one it rests against, the more important is the second, the one you do not notice. At Malpasset, the natural dam is where the whole story lives. Here is the trap, and it is a subtle one. The rock under Malpasset was gneiss, a hard metamorphic rock, and on the surface that looks like exactly what you want. But gneiss has a grain to it, a layering called foliation, the way a stack of paper has a grain. At this site, those layers were tilted, dipping downward in the downstream direction at an angle of somewhere between 30 and 50 degrees. And running through that rock, just downstream of where the dam would sit, was a geological fault, a fracture in the ground oriented roughly across the valley. Neither of those features was visible from the surface in any way that alarmed the people who looked. And the people who looked did not look very hard. Funding for the geological investigation was thin. The survey was, by the standards even of its own time, light. A more thorough study might have mapped the foliation and the fault and asked the dangerous question. Nobody asked it. Construction began in April of 1952. The dam was substantially complete by 1954, and the site's real geometry, that tilted grain and that hidden fault, stayed a secret in the ground. There was one more piece. On the left bank, the natural rock did not rise high enough to anchor the arch where the design needed it. So the builders added a large concrete structure beneath that end of the dam, a wedge-shaped block called a thrust block, to raise the abutment to the right height and receive the arch's push. Remember that block. When Malpasset failed, it failed there first. Now let me walk you through the mechanism, because this is the part that changed my entire profession, and it is not obvious. When the reservoir filled, the water did two things at once. The first is the thing everyone expects. It pushed on the face of the dam, and the arch carried that push down and sideways into the abutments, exactly as designed. But water does a second thing that is far quieter and far more dangerous. It seeps. It works its way down into the rock beneath the foundation, into every crack and joint, and once it is down there, under the weight of a full reservoir, it pushes upward. Engineers call this uplift. It is the pressure of water trapped beneath a structure, trying to lift it off the ground. Every dam foundation on Earth deals with uplift. The way you deal with it is drainage. You give that trapped water an easy path to escape so the pressure can never build. Under a thick, heavy gravity dam, the practice of the day leaned on the dam's own weight and some drainage to hold everything down. Under Malpasset, which was thin and light and depended entirely on the rock, that same reasoning was applied to a foundation that could not afford it. What the investigators pieced together afterward is that the immense force of the arch, concentrated on that tilted gneiss, did something almost nobody at the time understood was possible. As the rock was squeezed under the load, it became less permeable, not more. The pressure closed the tiny pathways that would have let water drain away, so a curtain of nearly watertight, compressed rock formed under the dam, and behind that curtain, on the upstream side, the seeping reservoir water had nowhere to go. The uplift pressure climbed and climbed, and it was pushing up against a block of rock that the geology had already cut loose on two sides, the tilted foliation forming one face, sloping down and away, and the fault forming the other. Together they defined a wedge, a three-dimensional block of rock beneath that left abutment, a shape geologists later called a dihedron, held in place only by friction and the strength of the rock around it. The rising water got underneath that wedge and lifted. And once the uplift force grew larger than everything holding the wedge down, the wedge moved. The ground the thrust block was standing on simply shifted out from under it. This is the failure the design never accounted for, because the tools to even analyze it did not fully exist yet. There were no instruments buried in the rock to measure that uplift pressure. There was no monitoring system watching the abutment for movement. Malpasset was built, and then it was essentially left alone. The design firm's formal involvement ended when construction did, and remarkably, the finished dam was never subjected to the kind of independent safety inspection we would consider mandatory today. For its first several years, the reservoir could not even fill completely, held back by an unresolved property dispute over a mine upstream and by a water network downstream that was never finished. So the dam sat, mostly empty, quietly waiting, with the flaw in the rock beneath it undisturbed because the full load had never once been applied. Then came the autumn of 1959, and the load arrived all at once. Between the 19th of November and the 2nd of December, roughly 50 centimeters of rain fell on the region. In the final 24 hours alone, 13 centimeters came down. The Rairen, dry for most of the year, roared, and the reservoir that had never been full in 5 years filled to the brim in days. By the 2nd of December, the water was reported to be within about 28 centimeters of the very top of the dam. For the first time in its life, Malpasset was carrying everything it was ever designed to carry, and more, and it was carrying it against a foundation that had never been tested at that pressure. And here the story turns from engineering into something harder to forgive, because the dam had been trying to warn people, and the warnings went into the same place bad news usually goes. In the weeks before, cracking noises had reportedly been heard near the structure. They were not investigated. In November, leaks appeared on the right bank of the dam, and by several accounts they grew rapidly in the days that followed, which for any engineer is a signal that water is finding a path it should not have. They were noted, and they were not acted upon in any way that reached the people living downstream. Think about what was missing here. There were no gauges in the foundation to tell anyone that the uplift pressure was climbing. There was no independent inspector standing at the site with the authority to stop the filling. The dam had reached its first true full load, the single most dangerous moment in the entire life of any dam, the moment when every assumption in the design gets tested for real, and it reached that moment essentially unwatched. The people near it could hear the rock talking. They just had no instrument that could translate what it was saying, and no procedure that treated a strange noise and a growing leak as the emergency they were. And on that final day, the man responsible for the dam, its guardian, André Ferro, could see the water climbing toward the crest and understood the danger. He wanted to open the discharge valves and relieve the pressure. He asked for permission to do it. He was refused. Downstream, crews were building a bridge for a new highway, and opening the valves would have sent water across that construction site. To protect the bridge works, the order to open the valve was withheld until 6 o'clock that evening. By the time Ferro was finally allowed to release water, the reservoir was so high that the valve, moving only about 40 cubic meters a second, could barely lower the level a few centimeters over the next 3 hours. It was like bailing an ocean with a bucket. And to make the trap complete, a telephone strike meant the Guardian could not simply call for help. Accounts describe him riding a small motorbike through the storm to carry the warning himself. The systems that were supposed to catch this, the inspection, the instrumentation, the ability to lower the reservoir, the ability to raise an alarm, had every one of them failed or been overruled before the rock ever moved. At 13 minutes past 9 on the night of December 2nd, 1959, the wedge beneath the left abutment gave way. The thrust block lost the ground it stood on, and the arch, which had been faithfully carrying its enormous load sideways into that corner, suddenly had nothing to lean against. An arch that loses one of its abutments is not a strong shape anymore. It is a line of heavy blocks with nothing holding them in compression. The failure ran across the dam almost instantly. Witnesses far enough away to survive described a flash and a sound like an explosion, and then the wall was simply not there. The whole structure came apart in seconds, and 50 million cubic meters of water that had been held back for 5 years was released in one motion into a narrow valley. What came down the Ririn Gorge was a wall of water reported at around 40 meters high, moving at something close to 70 kilometers an hour. It did not flood the valley so much as scour it. It stripped the ground bare for kilometers. It tore blocks of the shattered dam loose, some of them weighing 600 tons, and carried them more than a kilometer downstream like gravel. The two small settlements directly below, Malpasset and Boson, and the highway construction camp, were directly in its path and were essentially erased. Many of the workers there, some of whom may never have been formally counted, had no chance at all, and then the wave kept going, out toward the coastal plain and the town of Fréjus, about 10 kilometers away. It reached the edge of the town in roughly 20 minutes. 20 minutes is almost nothing. It is not enough time to understand what is happening, let alone to run from it, and there was no working telephone line to carry a warning ahead of the water anyway. By the time the flood arrived, it had spread across the plain and lost some of its height, but it was still standing something like 3 meters high when it swept into the western half of Fréjus. It went through homes where people were asleep, through the railway station, over roads and rail lines, tearing away more than 2 kilometers of track and cutting the coastal railway that linked this stretch of the Riviera to the rest of the country. It swept through farmland, destroying hundreds of small farms and, in a detail that says something about the region it drowned, tens of thousands of hectoliters of the local wine. And then, finally, it reached the Mediterranean and went still, as if nothing had happened at all. The most consistent figure for the dead is 423. I want to slow down on that number because the competitor's instinct in my field is to say it once and move to the lessons, and these people deserve more than that. Of the 423, 135 were children under the age of 15. Another 15 were teenagers. 134 were men, 112 were women, and 27 people were so completely taken by the water that they were never identified at all. 79 children were left orphaned in a single night. Around 7,000 people were left homeless. The wave cut every road, every telephone line, every water and power connection into Fréjus, so that a town of that size was, for a time, simply severed from the rest of France. And there is a detail that tells you how young many of the dead were and how suddenly it happened. In the aftermath, France extended a rare provision that allowed a number of women who had lost the men they were engaged to marry to be married to them posthumously. That is the kind of grief this left behind, not a statistic. Weddings held for the dead. The man who designed the dam did not escape it either. André Coyne, the most honored dam engineer in Europe, the man who had said no arch dam had ever failed, lived to see his fail and to see the bodies pulled from the Reyran Valley. He died the following year, in 1960, by many accounts, a man broken by what had happened at Malpasset. He had spent a career warning that the natural dam, the rock, was the more important of the two, and he was undone by exactly the thing he had spent his life pointing at. The investigations took years, and they landed somewhere uncomfortable. A great deal of forensic work, rock mechanics testing, and expert analysis eventually reconstructed the mechanism I just described. Uplift, driven by the reservoir, moving a rock wedge defined by the fault and the tilted foliation, dislodging the left abutment. When the case reached France's highest court in 1967, it concluded that there was no criminal human fault to assign, that the failure came from a geological reality nobody at the time had the tools to see. And in a narrow legal sense, that is true. The rules that would have caught this did not exist yet, but the technical community that studied Malpasset for the next 50 years reached a harder and more useful judgment. The site investigation was inadequate. The foundation was never instrumented. The uplift in a thin arch dam's foundation had never been taken seriously enough. These were not the crimes of one villain. They were the blind spots of an entire profession, and Malpasset is where the profession finally saw them. Because here is the part that matters to you, wherever you are watching from, and it is the reason this obscure French dam is one of the most important failures in the history of my field. Malpasset is the disaster that created modern rock mechanics. Before December of 1959, the behavior of the rock under a dam, the faults, the foliation, the uplift pressures moving through it, was treated as a secondary concern. After Malpasset, it became a science of its own. Engineers began systematically analyzing the stability of rock wedges beneath abutments, the exact failure that took this dam. They began drilling drainage into arch dam foundations to kill uplift before it could build. They started treating the first filling of a reservoir as the delicate, closely monitored operation it always should have been, watched by instruments that can feel the foundation move a fraction of a millimeter. France created a permanent national committee to oversee dam safety, so that no finished dam would ever again simply be handed over and forgotten. Around the world, the way we investigate the ground beneath a dam, the faults we hunt for, the wedges we test for, the uplift we design against, was rewritten, and it was rewritten in response to this one small river valley in the south of France. Every arch dam built since, and there are many, far taller than this one, that have stood without failing, stands in part on what was learned from the 423 people who died below Malpasset. I started by telling you that the dam did not fail. Let me be precise now about what I meant, because it is the whole lesson. The concrete did not fail. The arch, as a piece of design, did not fail. What failed was the assumption underneath it, the belief that the ground could be trusted because it looked solid when nobody had done the work to know. The engineering that everyone could see was close to perfect. The engineering that nobody could see, the natural dam, the rock, the wedge, the uplift, was never really examined until it was too late to matter. André Coyne told his students that of the two dams, the important one is the one you do not notice. Malpasset is the proof of that sentence, written in the worst possible ink. The blocks are still out there in the Reyran Valley, too heavy to move, slowly weathering in the sun above Fréjus. People walk out to see them, and I think that is right, because a failure like this one should not be allowed to become abstract. 600 tons of concrete sitting a kilometer from where it was cast is a hard thing to argue with. It tells you, plainly, that the ground has the final say, and that the job of an engineer is not only to build the thing you can see, but to understand the thing you cannot. Malpasset is the bill that came due when we forgot that. 423 people paid it, on a rainy night in December, in seconds, and the least we owe them is to never again mistake a quiet foundation for a safe one. I'm Dr. Michael Carter, and this has been the story of the Malpassé Dam. Watch the water and look twice at the ground everyone swears is solid. I'll see you next time.